Welcome to Barrel Section 10, and this is spinning. My name is Fibre, and I'm from the Textile Institute of Pakistan in Karachi. In today's session, we have 5 topics relating to spinning. As I just mentioned, we have 3 speakers. Moment, maybe there are 2, but we will start since we have the first 2 speakers. Now, before we start, can I again request all our delegates to please switch off their mobile phones they have with them. It is quite disturbing for the speakers. The concentration tends to go. So please, could I request you all to switch them off. And for those of you who are using the translating system, you know how it's running. Now, all the speakers will be given 15 minutes for their presentation, followed by, if we have time, for 1 question. And we can always have another question and answer session at the end if there is time permits. So we start with our first speech today, and this is it's on the effect of modification and processing variables on yarn formation and characteristics in monocylinder friction spinning. The main author of the paper is Dr. Mostafa from the Cotton and Textile Industries Holding Company. But unfortunately, he cannot be here, and on his behalf, we have Engineer Ali Abdul Rahman from the same department. He's the head of the research and development sector at the Cotton and Textile Holding Company. So on behalf of Dr. Mostafa, can I request Mr. Abdul Rahman to present his paper.
Ladies and gentlemen, good afternoon. It's a very great pleasure to welcome so many distinguished guests and speakers from all over the world to this 82nd World Conference of the Textile Institute. I have the honor to introduce myself, Engineer Ali Abdul Rahman, Research and Development Sector Head, Cotton and Textile Industries, Holding Company, on behalf of Dr. Muhammad Hassan Mostafa, the Chairman Deputy of the Cotton and Textile Industries Holding Company, and one of the gentlemen whom issued this paper about the effect of modification and processing variables on yarn formation and characteristics in mono-cylinder friction spinning. Dr. Mostafa would like strongly to share this session, but although he was obliged to be out of Egypt for very urgent business since yesterday, he wishes for you and for me all the best. Again, I would like to welcome all of you to this lecture. The introduction. In recent years, one of the newest spinning systems became an important factor of textile research, that is the friction spinning system. This system usually consists of 2 juxtaposed rotating cylinders that produce a torque load for the twisting of fibers into yarn. Transparent will show you a brief explanation of the machine. That's Dr. Mostafa. the parts of the machine. This assembly of the machine, the next one. And this diagram sketch of the machine assembly. The earlier studies reported that the fiber should be considerably individualized with good orientation parallel to one another and to the yarn axis. The effect of fiber feeding arrangements and opening roller speed on the properties of frictional span yarn. The prototype experimental unit has been modified to be Modispinner 2, monocylinder friction spinning machine, and used throughout the experimental work of the parameters considered, which are the slit angle, the suction force, the monocylinder speed, and the opening roller speed for 2 yarn counts. These related to yarn linear density are the variables that affect yarn hardness, irregularity, and imperfections per 1,000 meters, as follows. Monocylinder speed, RPM 3,000, 3,500, 4,000, 4,500. Slit angle 0 degree, -5, +5, +10. Suction force, kilopascal 4.2, 5.9, 8.4. Opening roller speed, RPM 6,000, 6,500, 7,000, 7,500. Also, there is an optimum value for slit angle. Suction force depends on the interaction with monocylinder speed. In this part of the experiment, the researchers intended to use the factorial design to investigate the interaction effect between the variables and determine the optimum processing conditions which affect yarn hardness. Experimental work, the following factors represent the main parameters in the study. Monocylinder speed RPM x1, suction force kilopascal x2, and slit angle theta x3 to study the main effect and their interaction. Experimental analysis, the results obtained for yarn hardness, irregularity, and imperfections were used in which the effects of slit angle, suction force, and monocylinder speed were assessed for 2 yarn counts, 6 LE and 18 NE. The results were fed to personal computer and regression coefficients were determined. The coefficients were tested for significance at the 95% significance level. Results. Yarn hardness. The effect of air suction force x2, slit angle x3, and monocylinder speed x1 for different yarn linear densities. The contour lines are saddle shaped with minimum and maximum falling inside the experimental field. The contours for yarn count number NE6 clearly show that the yarn hardness increases at the lower rate of slit angle and with the increase of air suction force and decrease with the increase of monocylinder speed. On the other hand, the yarn hardness at 3 mm decreases at higher value of slit angle and interaction between the maximum value of suction force and minimum value of monocylinder speed and vice versa. For yarn count number 18, the contours for yarn hardness which conform a saddle to a saddle shape, whereas an increase in slit angle and suction force causes it to decrease. This can be explained by the increase in slit angle result in better fiber straining and configuration during yarn formation. Consequently, this leads to increase in the effective length inside the yarn and causes better configuration and low hardness. The minimum incidence of yarn hardness seems to be okay at a slit angle 2.5 degrees and suction force 7 kilopascal. Also, increasing of monocylinder speed, especially at higher slit angle, results in increase of yarn hardness. This trend may be explained by the influence of combination centrifugal force at higher speed, frictional and aerodynamic. In fact, the aerodynamic forces due to higher rotational speed and the regression of yarn formation result in higher protruding fibers from yarn body. Second, yarn regularity. The effect of slit angle, suction force, and monocylinder speed for different yarn count, for two, in matter of fact, two yarn count on yarn irregularity. What's the percentage? For yarn count number 6, there is a clear-cut minimum for the tested yarn. The minimum occurs at suction force lie between 7 and 9.8 kilopascal, but the optimum slit angle depends on increase of monocylinder speed. The minimum occurs at slit angle minus 10 for monocylinder speed 3000. Slit angle, plus 10 for monocylinder speed 3000, slit angle for speed 10 for speed 3.75 RPM, and slit angle 2.5 for speed 4,500 RPM. The contours of yarn irregularity for yarn count number 18, which conform to saddle shape, whereas an increase in slit angle at different levels of suction force increases the yarn irregularity. The lower rate of yarn irregularity has been observed at lower values of slit angle and suction force between 7 to 11.7 kilopascal. Also, the results indicate that a slight change on yarn uniformity attainable with increasing monocylinder speed. Yarn imperfections, thin places per 1,000 meters. The minimum value of thin places per 1,000 meters of friction occur at slit angle between 2.5 and 10 degrees for yarn counts number NE6 and NE18 respectively. The optimum of suction force depends on the interaction with the monocylinder speed. For yarn count NE6, the minimum thin places occur at suction force 4.2, 8.4 kilopascal and 9.8 kilopascal for monocylinder speed 3,000, 3,750 and 4,500 RPM respectively. On the other hand, for yarn count NE18, as shown, the minimum values for thin places occur at suction force 7 kilopascal for all monocylinder speed values. Thick places per 1,000 meters. The minimum value of thick places occurs at slit angle 2.5 degrees, either with varying suction forces or and monocylinder speed. This associated with yarn count NE6. For yarn count NE18, the increase in suction force decreases the number of thick places per 1,000 meters. Also, it decreases with an increase of slit angle, especially at high level of suction force. The minimum occurs at the slit angle 10 degrees, but the optimum of suction force depends on the interaction with monocylinder speed. The minimum occurs at the suction force of 11.7 for speed 3000 RPM and slit angle 9.8 degrees for cylinder speed 3750 RPM and slit angle 7 degrees for monocylinder speed 4500 RPM. NEPS per 1000 meters. For yarn count number NE6, the experimental results explore that increasing slit angle and air suction force causes a significant improvement in NEPS per 1000 meters. Also a lower number of it has been declared at higher mono-cylinder speed for yarn count NE6. The minimum occurs at a slit angle varies between 2.5 and 14.6 degrees, but the optimum suction force depends on the variation in monocylinder speed. The minimum occurs at suction force of 7 and 9.8 and 11.7 kilopascal for monocylinder speeds 3000, 6750 and 4500 RPM respectively. On the other hand, for yarn count number LE18, the results indicate that increasing monocylinder speed from 3000 to 4500 RPM results in an increase in NEPS per 1000 meters. The increase in slit angle at lower values of air suction does not show any effect on the number of NEPS, while it causes an increase in NEPS at higher level of air suction force. The lower yarn imperfections NEPS has been observed at suction force 7 kilopascal. This trend occurs with varying slit angle or and monocylinder speed. Now to the conclusion. The present study permits the following conclusion to be drawn. The slit angle is a fundamental aspect of this method of spinning. It creates the necessary position of fiber feed tube relative to the friction surface. These lead to control the number of fibers landing directly on the rotating tail over perforated monocylinder surface. Without that, proper configuration of the staple fibers would be impossible. It has a considerable effect on mass variation, irregularity to the percent, and yarn hardness of friction spun yarn. Due to better fibers threading, which leads to increase the effective fiber length inside the yarn and consequently better fiber configuration during yarn formation. With an increase of slit angle, the hardness level, yarn irregularity, and yarn imperfection force. Air suction force within the limit of the present experiment leads to the achievement of the desired yarn counts. Higher values of suction force reducing the ratio of slippage between the yarn circumference and monocylinder friction surface, and so more twists will be imparted. It produces more compact yarn structure. Also, it has a significant effect on yarn hardness and irregularity. Monocylinder speed has a significant effect on yarn evenness, and a lower number of NEPS per 1000 meters are attained at higher speed for coarse counts, while it brings about deterioration in yarn imperfection for finer counts. The minimum values of yarn hardness and imperfections, as well as better yarn uniformity, occurs at the optimum slit angle and suction force, which are at higher values over 2.5 degrees and around 7 kilopascal respectively, and mono cylinder speed lie between 3,000 and 4,000 RPM. We use material Giza 85, and the variables are, as I mentioned, the monocellular space at angular section force of nucleus. Thank you.
Thank you, Engineer Abdurrahman. Since Abdurrahman is just presenting on behalf of Mostafa, and in the interest of keeping time, we leave the questions to the end. I'm not sure whether they will be able to answer our questions.